In today's class also, we are going to continue our discussion on validity of closed graph theorem and open mapping theorem. If X is not a Banach space and Y is a Banach space, then open mapping theorem fails. Example, consider an infinite dimensional separable Banach space. An infinite dimensional separable Banach space Y. For example, you can consider Y to be little LP for some P with 1 less than or equal to P less than infinity. Let set of all Ys such that S belongs to S be a Hamel basis for Y. Since Y is a Banach space, by 8.4 S is an uncountable set. Then S is an uncountable set by 8.4. Let X denote the set of all scalar valued functions on S, which vanishes at all but finite number of elements of S. Then X is a linear space over K under point-wise addition and scalar multiplication. For X in X, let norm of X equal to sigma S in S modulus of X of S. Then norm is a norm on X and X is not separable. Note that X is not separable, since for fixed S in S, let xs of t is delta st, t belongs to S. Then set of all xs such that S belongs to S is an uncountable set in X, and norm of xs1 minus xs2 equal to 2 for S1 not equal to S2. This is because norm of xs1 minus xs2, this is equal to sigma t belongs to S modulus of xs1 of t minus xs2 of t that is equal to sigma t belongs to S delta S1t minus delta S2t. When S1 and S2 not equal to t, delta S1t, delta S2t are 0, and when t is equal to S1, we get this is equal to delta S1 S1 minus delta S2 S1 plus when S2 equal to t, you will get delta S1 S2 minus delta S2 S2. So this is equal to modulus of 1 plus modulus of minus 1, so this is 2. Therefore X is not separable. Now for X in X, define f of X equal to sigma S belongs to S X of S into Ys. Then f from X to Y is a linear map and f is continuous, since norm of f of X, this is equal to norm of sigma S belongs to S X of S into Ys less than or equal to sigma s belongs to s modulus of x of s into norm ys. You know that norm ys is 1, so this is equal to sigma s belongs to s modulus of x of s, so this is equal to norm x. That is norm of f of x less than or equal to norm x for all x in x. Therefore f is continuous, and being continuous f is closed also. Therefore f is continuous, and being continuous f is closed. Also f is bijective, and f is not an open map. If f is an open map, then for E open in X, f of E is open in Y. So this implies f inverse from range space of f to X is continuous, since for open set E in X, f inverse of E, that is equal to f of E, is open in range space of f. That is, if f is open, then f from x to y is already continuous, and f inverse from range space of f to x is also continuous. So this implies f is a homeomorphism. That is, f from x to y is a homeomorphism. We know that x is non-separable normed space and y is a separable normed space. So that is, f is a homeomorphism from a non-separable normed space x to a separable normed space y, which is not possible. Therefore f is not an open map. That is, we have f from x to y, where y is a Banach space, is closed and surjective, but f is not open. This in fact imply that x is not a Banach space. Thus we have an example in which the open mapping theorem fails. So the open mapping theorem fails when x is not a Banach space and y is a Banach space. Now we are going to give an example to establish the fact that the closed graph theorem may not hold if the range space is not complete, although the domain space is complete. We are continuing with the same example. Since f from x to y is closed bijective, is closed and bijective, f inverse from y to x is also a closed map. However, f inverse is not continuous, since f is not an open map. This is because since if f inverse is continuous for open set E in X, f inverse of E is open in Y. So this implies f of E is open in Y, which is not possible since f is not an open map. F is not an open map. That is, f inverse from y to x is a closed linear map, but F inverse is not continuous. That is, even though Y is a Banach space, closed graph theorem fails if X is not a Banach space. That is, the closed graph theorem fails if the range space is not complete, although the domain space is complete. Here you know that the range space is X and the domain space is Y, and X is not Banach, Y is Banach. That's all for today. Have a nice day.